Hello, good morning. This is going to be the next set of notes from the professor in Microbio. So this was like the chapter over organic acids and how they're made. So the first one is citric acid. 2.9 million tons were manufactured in 2023. There's the start of the production of citric acid in 1890 in Italy, and it's from the citrus fruit industry. You would treat the juice with calcium hydroxide to precipitate calcium citrate, and then you convert that back to citric acid using sulfuric acid. In 1893, they found out that penicillium would be able to make it from sugar. World War One didn't really World War One until that time, it wasn't very industrially important to make it until we get to World War One when you had the citrus supply getting interrupted due to all the conflicts. So then they had to switch to the mold and the microbes. Some of the uses, of course, include the usage in drinks, candy cleaning. You could chelate metals to remove limescale. You could also use it in cosmetics and pharmaceutical industry. There's acidulant in creams and gels, dietary supplements, chemical peels, and iron citrate is used to preserve blood. Sorry again if I sound a little bit under the weather, that's why. That's because I am right at the moment, and yeah, I don't like it a bit. Okay, the microorganism. It's going to be Aspergillus niger. And this mutant will be used because it makes more citric acid per unit of time. And undesirable byproducts such as oxalate are also efficiently suppressed by using an Aspergillus niger mutant. Biochemistry, so this is going to be all the pathways. And so one pyruvate molecule will enter the mitochondria, and it's going to be converted to acetyl-CoA. The other pyruvate is converted to oxaloacetic acid, and then it's reduced to malate via transported. And that malate is transported into the mitochondria by a carrier where the oxaloacetate is regenerated. And then the oxaloacetate condenses with acetyl-CoA to form citric acid. That's the first step of the TCA cycle. And now the citric acid leaves the mitochondria, but you need this specific carrier, this citric acid carrier, to leave the cell. Solid surface, so they're going to be using solid surface, one of the ways to make this fungi and then harvest its citric acid. So you're going to be using wheat bran or sweet potato starch pulp as the medium. The spores are then spread. Then they're going to be on the trays. They're incubated at 28 degrees Celsius for 90 hours. And then use hot water to extract the citric acid. We also have this liquid medium surface process. And this is going to make 20% of the world's supply. You have low cost and low energy because you need to cool it. There's going to be this high labor cost. The medium is going to be 16 to 20% sucrose from beet molasses and 1.6 to 3.2 grams per liter of ammonium nitrate. We also have magnesium, calcium, and iron, as well as minerals. The medium is then pumped into the trays, and then you do it at 30 degrees Celsius for 8 to 14 days. Now let's talk about the submerged process. 80% of the supply of citric acid is made in this method. There's low construction, labor costs, and there's a greater energy cost, unfortunately. So 3 factors are important. The vessel material, it's an acid that you're trying to collect, so you need stainless steel to prevent corrosion. Structure of the mycelium is also important. You need solid pellets. O2 supply, oxygen supply, you need a 20 to 25% concentration. And the aeration rates need to be between 0.2 to 1 volume for volume per minute. So, for an example, if it's 200, you pump 100 per minute. Fermentation. So the feedstock now, 15 to 25% starch, glucose, and cane syrup. You also need minerals such as copper, iron, magnesium, and zinc. However, going back to the carbs quickly, you could get it from starch hydrolysates, glucose syrup, and cane syrup. Okay, now back to the metals. You need to be deficient in manganese. However, the ratio of iron to copper is going to determine the mycelium structure. Remember, we want small pellets. You need high concentrations of ammonium ions as well. The temperature, again, it's about 30 degrees Celsius, which we saw. Aeration rate, 0.2 to 1 volume minute. Okay, oxalic acid recovery. So you're going to be using calcium hydroxide to precipitate out oxalic acid. You're going to be using these rotating filters to remove the mycelium and the calcium oxalate. And then the citric acid is precipitated at pH 7.2 and 70 to 90 degrees Celsius. Then you're going to dry it using the rotating filter. And then for higher purity, you could dissolve it in H2SO4. Then the calcium sulfate precipitates out. Then you ion exchange the liquid, and then you concentrate by evaporating, and then you crystallize the citric acid. Okay, now acetic acid. As long as there's been wine, there's been this acetic acid from alcohol 10,000 years ago. So what it is, it's basically this drink of diluted vinegar that was used by the ancient Greeks and Romans. Then the Middle Ages, you used open vat methods. This is when the wine gets sour, so you have a film of bacteria on the side. The wine, 19th century, you saw the trickle generator process, and then 1949, they switched to the submerged process for acetic acid. So this is an incomplete oxidation rather than a fermentation. Again, the reducing power is transferred to oxygen. So step 1 is when ethanol is converted to acetaldehyde. Hydration is this next step where acetaldehyde becomes this acetaldehyde hydrate. And then step 2, you have acetaldehyde hydrate becoming acetic acid. You need a lot of O2 here for optimum performance. However, you need to be wary because tons of O2 as well as high alcohol. Oh wait, sorry, I got that backwards. High alcohol and low O2 will cause the cells to die. The microorganism would be a gluconobacter, which is gram-negative rod. It could go from ethanol to acetic acid. Acetobacter, however, goes from ethanol to acetic acid, then to CO2 and H2O. So you need to use a mixed culture. You're going to have a mini reactor so they don't change genetically or lose yield when dealing with these mutants or strains. Let's talk about the surface process. This is going to be used for household vinegar. You use beechwood shavings in the reactor, and you're going to spray alcohol on the surface. Then you're going to collect the alcohol in the basin and then recirculate it. Air is blown through the beechwood. And then the temperature is upper 29 to 35 degrees Celsius. In about 3 days, this is when the fermentation is going to be complete. Let's talk about submerged process. So the incoming air is sucked down by a rotor, and then you're going to have some heat exchange to control the temperature. There's a low capital cost, there's less area for installation, and a low operating cost because this could be fully auto. Let's talk about the conditions. You're going to start with 10% acetic acid, 5% ethanol. This is going to be added semi-continuously. And then when ethanol is down to 0.3% in about 35 hours, you're going to replace 50% with new mash, which is 2% acetic acid and 15% ethanol. Production rate is 10 times higher than a surface process if we use submerged. Recovery, the only thing there is you could clarify the acetic acid using plate filters to remove the cells of a gluconobacter and acetobacter. And then you're going to decolorize it with potassium ferrocyanide. All right, that's everything that the professor wrote down for acetic acid and citric acid. Please have a good day. Do something nice for someone. Take care.